All right. So, hi, everyone. It's a pleasure to host Shubhayu Chatterjee from UC Berkeley today for this seminar. So just in terms of a quick introduction, well, it turns out Shubhayu and I go back a long time. I've known him for almost 15 years now. And that's not to say that either one of us is that old. It's just that we overlapped as undergrad students in India, and then both of us were PhD students at Harvard with Subir. And Shubhayu has done a lot of interesting work over the years in a variety of different topics, and he continues to do new and interesting things ever since he's moved to UC Berkeley, including apparently starting to do DMRG himself. So he's going to tell us about some of this exciting new stuff today. Yeah, the floor is all yours, Shubhayu.
Right. Thanks, Devanjan, for the kind introduction. And indeed, it's a great pleasure to be here. I wish I could actually be on the campus giving this talk, which would have also allowed me to travel. But given COVID regulations, this is the best we can do at this point. Okay, so today I'm going to talk about Skyrmion superconductivity, which is a kind of interesting strong coupling route to superconductivity. And this work was mainly motivated by applications to moiré graphene platforms, in particular by twisted bilayer graphene. But the model and the phenomena or the mechanism are not really limited to twisted bilayer graphene. So I will first present a more generic and simplified model which abstracts away from some of those complications. And then I will introduce twisted bilayer graphene and how it fits into the story, and finally go on to some numerical evidence that this mechanism actually works beyond semi-classical theory, even when you put in quantum fluctuations. Okay, so before beginning, let me acknowledge all my collaborators. We have been collaborating with all these fantastic people. So with Matteo at Stanford on the DMRG, Eslam and Ashwin on a lot of theoretical aspects, and with Nick and Mike, who have been my collaborators since I started my postdoc, and it's been fantastic working with them. And the work has appeared in these 3 papers, which you can take a look at later. Okay, so I will start with the simplest setting or the simplest model in which such physics may be seen. So that setting is just take 2 sets of spinful Chern bands, say 2 with Chern +1 and 2 with Chern -1, and there is an internal degree of freedom within each Chern sector. And these bands are nearly flat so that the interactions dominate over dispersion. And then consider tunnel coupling these 2 bands. So that's the basic model I will focus on for the rest of my talk. But when I will discuss twisted bilayer graphene, I will try to motivate why this might apply there. And within this model, let's consider a half-filled state, which is to say I fill 2 out of 4 bands. So in absence of this tunneling between the bands, so if we just turn it off, then as expected from the Stoner criteria, we are in the flat band limit. So the density of states is practically infinite in the thermodynamic limit, and we get some kind of ferromagnetism. So in each Chern sector, we will get a ferromagnetic state, which with a spin pointing in some particular direction, there is full spin rotation symmetry within each Chern sector, let's say. So without any coupling between these 2 sectors, the spin directions are not a priori determined. Now let's add back this tunneling and see what we get. So once we add back this tunneling, we see that there is some hopping process in between the Chern sectors. Now, starting with the ferromagnet, if the hopping is weak, then if the spins are pointing in the same direction in both the Chern sectors, then this hopping will be Pauli blocked. However, if the spins are pointing in opposite directions in these 2 Chern sectors, then this coupling can lead to an antiferromagnetic super exchange, which is very much similar in spirit to the Anderson super exchange, except that here we cannot really have localized Wannier orbitals. So this is a description, if you want to think of it, maybe in momentum space or with 0th Landau levels, Landau gauge wave functions. So this tunnel coupling actually just acts as an antiferromagnetic exchange in the small h over interaction limit. And this induces a term which is like Jn plus dot n minus, where plus and minus are the two Chern sectors, and n plus and n minus refer to the spin directions. So the ground state at half filling, or 2 out of 4 bands, in presence of this tunnel coupling and large interactions, is a spin layer locked insulator. This is a ferromagnet in each Chern sector and antiferromagnetic in between the Chern sectors. I will often call it an antiferromagnet, but keep in mind that there is no actual magnetic moment, because there is the net magnetic moment when we combine the two Chern sectors just cancels. Okay, so we can write down a more concrete Hamiltonian for this, which is just take interacting electrons in 0th Landau levels, but with opposite magnetic fields. So consider a bilayer Landau level problem where I have like plus B magnetic field, let's say, in one layer and minus B magnetic field in the opposite layer. Of course, this is not feasible to have in a quantum Hall system, but we will see how such fields may naturally arise in TBG. And the Hamiltonian is basically the sum of the kinetic term. Here, gamma refers to the layer index, and the layer, and in each layer we have opposite fields, which is taken into account by this gamma z multiplying the vector potential. Then there is the Coulomb repulsion in between the electrons. And finally, there is another additional term, which I kind of put in by hand because these Landau levels do not have any dispersion, but this will be generated if I also put in dispersion in these Landau levels. And that term is an antiferromagnetic super exchange, which is the psi dagger gamma z eta psi. So eta here is the spin degree of freedom, and multiplying by gamma z means that this interaction is antiferromagnetic. So I've also allowed for some anisotropy here, which will kind of be important for TBG. So there is an isotropic super exchange, of course, where Jx equals Jy equals Jz. But we can also allow for some easy plane or easy axis anisotropy by adding some term lambda, which breaks this SO3 symmetry to U1. So at 2 out of 4 filling here, again, as we discussed, we expect an antiferromagnetic insulator. And it turns out that this insulator actually preserves Kramer's time reversal symmetry, which is generated by this gamma x eta y, so times complex conjugation. So we generally expect robust pairing of fermions, which are related by this Kramer's time reversal symmetry in this state. Oh, by the way, so I forgot to mention this, but feel free to interrupt me and ask questions at any point of time. Okay, so as we discussed, there is some Kramer symmetry, so there can be some pairing between Kramer's pairs, which would be robust. But are these pairs necessarily electron pairs? So that would be the case if these were not Chern bands. For regular bands, the natural low energy charged excitations to consider are particle hole excitations. But because these are Chern bands, they can have additional topological textures, which also carry charge. So in particular, there are Scurmions in each Chern sector or layer, which carry some charge. And these Scurmions are objects classified by the second homotopy group of the sphere. And these, therefore, one can associate a winding number to these Scurmions, which I call Q topological. And the physical charge of the Scurmion is the product of the Chern number of the band times the topological winding number of the Scurmion. So this naturally leads to certain interesting questions. So the first question is, assuming that these charged Scurmions are energetically relevant, which means that I need to have low spin stiffness because these Scurmions are basically twists in the spin texture. Can they naturally bind together into 2e pairs? Because they are charged, they will tend to repel. So there needs to be some physical mechanism responsible for binding. if there are 2e pairs, the second question is if these can give rise to superconductivity on doping the half-filled insulator. So if there are 2e low energy excitations, what happens on doping? That's not very obvious because 2e pairs may even be present, but in presence of a strong magnetic field, like in quantum Hall systems, we would expect their kinetic energy to be quenched, which means that they are not mobile, they're not doing something very interesting. And the final question is, if there is indeed superconductivity, what sets TC for the BKT transition? Or in other words, in terms of these 2e pairs, what sets the mass of these 2e pairs, or how do they disperse?
So Shubhayu,
Yeah.
maybe you will go into this at great length, especially when you talk about TGG, but I have a very basic question here.
Right.
So, I mean, I guess, of course, we know that if we dope the system, there can be a Skyrmion superconductor in principle. But in order for this to be experimentally relevant, should there be somewhere in the phase diagram where the Skyrmions are in fact the cheapest excitations, or is it okay to not have any the Skyrmions actually being the cheapest excitations anywhere and still expect the dope system to show a Skyrmion induced superconductor?
Right, so that's a very good question, and here to answer this I have to distinguish between charge E Skyrmions and charge 2e Skyrmions.
Yeah.
So it could turn out that charge E Skyrmions are more expensive than just charge E electron excitations.
Right.
And that would be okay. However, if the charge E Skyrmions gain sufficient energy by binding, so that energy becomes much lower than what 2 charge E electrons would gain out of binding, then these charge 2e pairs could be present and they could conduct, they could superconduct.
Right, but is there a sharp distinction you can make between a charge 2e Skyrmion and the Cooper pair that has perhaps a big size or whatever?
So as far as the symmetries are concerned, the answer I think is no, because there is only an energetic distinction here,
right.
No symmetry distinction. So even though the mechanism is somewhat different, I think at the end of the day, the superconductor you will get out of it can be, just thought of as S wave or P wave in terms of the same terminology as far as symmetry of the superconductor is concerned.
Okay, I might come back to this later on as the talk goes on. Thanks.
Okay, so to answer questions 1 and 3, we might appeal to a semi-classical description of these Skyrmions in terms of some nonlinear sigma model for the order parameter. But question 2 turned out to be particularly hard to answer. So before I go into details, I should definitely mention that superconductivity from 2e Skyrmion condensation is not new. This has been proposed in seminal works by Abanov and Wigman, and later by Grover and Senthil in doped quantum spin Hall insulators. And also very recently, there has been a paper from Fakhar Asad's group, this last paper, Wang et al. I should have updated, it just got published in PRL. And they do see that on doping quantum spin Hall insulators, there is some superconductivity. And they see this in sign problem-free quantum Monte Carlo. But in order to keep the problem solvable or avoid the sign problem, they have to kind of neglect Coulomb repulsion in their model. So the same kind of mean field interaction, which gives them topological bands, when decoupled in the superconducting channel, also gives them superconductivity. So I guess the question we are trying to ask here is that what is the phase diagram at t = 0 once we do include Coulomb interactions? Or can Skyrmions pair even in presence of Coulomb interactions? This is not obvious, and they could, for example, at very low densities, go out to form Wigner crystals of 2e bosons. So we do need alternate numerical methods like DMRG, which we used and to study this problem.
Shubhayu, this might be a minor thing, but I missed this. If you completely throw out the Coulomb interactions for this QMC, how do you get the Skyrmion in the first place?
So you don't completely throw it out. You basically introduce a term in the Hamiltonian, which is an interaction term that prefers this quantum spin Hall insulator. So that's the term which gives rise to the mass of quantum spin Hall, the quantum spin Hall mass. So you start with Dirac fermions and then have a mass term. So this interaction is basically this mass squared, roughly speaking. But you can also decouple this interaction instead of in this particular channel in the superconducting channel. And at mean field level, I think we'll get superconductivity from that. So of course, this interaction originates from some kind of other more microscopic source, but that hasn't been studied, at least in this paper, as far as I know. Okay. So let's try to understand the energetics of these Scurmions to see first whether they can be relevant excitations, and if so, what is their effective pair mass. So first, let's focus on a single Skyrmion in one Chern sector, which is the top figure. So what are the energy costs for this particular object? Well, of course, it pays a stiffness cost. And if that was the only cost, then that would be independent of the size of the Skyrmion, as shown in this paper by Belavin and Polyakov long ago. But it turns out that there are other subleading effects which determine the size. And the first thing is that it pays some energy penalty because some spins are anti-aligned with the other layer here. So that's an exchange energy penalty it has to pay. So that would try to shrink the Skyrmion. But at the same time, it could pay, if it shrinks too much, it has to pay some Coulomb energy, just semi-classically. So it's the competition in between these two that actually determines the size of this Skyrmion. Now imagine a Skyrmion in one quantum Hahn layer and an anti-Skyrmion in the opposite layer, which also has opposite Chern number. So this can be achieved by just having a Skyrmion texture n of r, let's say in one layer, and just flipping the spin texture to minus n of r in the other layer. So because the physical charge is equal to the Chern number times the topological charge, and the topological charge is odd in n. So flipping the spin texture in between the two layers also means that I have opposite topological charge, but they also have opposite Chern numbers, which means that they carry the same physical charge. So these would be repelled by Coulomb interaction, but there is this local kind of antiferromagnetism J, which is perfectly happy with this arrangement. So it wants it to stay like that. And now they can spread out to become very large in size. So in an absence of any anisotropies, they will be potentially infinite in size to get rid of all Coulomb energy costs without losing any exchange interaction. So this leads to kind of a natural pairing mechanism, which is all electronic in nature, between these two chargey objects. So just as we were discussing earlier, it's not enough to have pairing. One also needs to have some superfluid stiffness, or in other words, these 2E objects need to have some dispersion. So chargey Skyrmions are also seen in quantum Hall systems, for example, but their kinetic energy are completely quenched by the magnetic field. So they do affect the spin susceptibility to some instance, but other than that, they don't do much interesting things. So what happens for the charge 2E Skyrmion? So this can be done much more formally, but here I will just give you a very intuitive physical picture. So note that these two charge 2E Skyrmion comes from charge E in each layer, and these layers see opposite magnetic fields. So which means that these charge 2E objects don't see any magnetic field, and therefore they can be mobile. And there's a kind of nice argument, modifying arguments for excitons in mass of excitons from Kalin and Halperin and by Kuhn-Yang, which can actually help us estimate the mass within a semi-classical picture. So take these two chargey Skyrmions and consider them moving with some center of mass speed v and at a relative separation of d. So the antiferromagnetic super exchange here is disturbed because I've separated them. And roughly the energy lost is proportional to d squared, because that's the area over which the spins are now misaligned. So the spring kind of force which tries to pull them together is proportional to the distance and the strength of this antiferromagnetic exchange. On the other hand, because these objects are moving in opposite magnetic fields, there is a Lorentz force which is trying to pull them apart. They have the same velocity, same charge, but opposite magnetic field. So the Lorentz force acts on opposite directions on these two. So by balancing these two, we can write down the energy as some V naught, which is the energy at zero separation, plus J times distance squared over 2, which is this kinetic energy, which is the potential energy cost for separating this. But D is directly proportional to the velocity. So by replacing that, we just get some dispersion. And the effective mass for this dispersion is proportional to inverse of J. That's kind of the key observation here. So once we know the scale J, we know what the pair mass is, and from there we can estimate TC.
So Shubhayu, can I ask a question?
Yeah.
So yeah, this I understand, but I'm just confused about one thing. So before you turned on the hybridization between the +-1 Chern sectors, you were assuming that they're independently at half filling. Did I get that right?
Yeah, so that's what I was assuming, and that's an important point. Let
me just finish my question. So
yeah.
Suppose you change the filling, you go to lower filling. I guess what I want to know is, what happens when you change the electronic filling in the different Chern sectors? And then, like, I mean, I'm confused only because, like, does the picture only apply at half filling, or does it continue to apply even away from half filling, but then the electronic density has to somehow show up in TC?
Right, yeah, that's a very important question. I kind of sidetracked this, but you have brought me back to it, so let me discuss it now. So you are right that, like, here I made an implicit assumption that I half fill each of the Chern sectors, but I might have filled one Chern sector fully and not fill the other one at all, and that would be a quantum Hall state. So that state is certainly allowed. What happens in this particular model is that, or also interested by graphene, by which this is somewhat inspired, is that there are other anisotropy terms in the interaction, which I haven't explicitly mentioned here, which prefers electrons to evenly distribute in between the two Chern sectors. So one way to think of it maybe is, like, I have some Coulomb interaction in between the layers, but let's say the Coulomb interaction in layer is larger than the Coulomb interaction in between the layers. Then the charges would like to distribute evenly in between these two layers. And that would be a scenario where at 2 out of 4 filling, you would prefer to, like, half fill each of the Chern bands.
Right, that I'm perfectly happy with. That was not my question. But I'm saying, suppose both sectors are evenly populated, but the actual filling is very low.
So you want to work away from half filling, basically?
Yes,
right.
Yes, go to very low filling. And at some point, the TC will be limited by the small electron filling. And I mean, does that just enter trivially in this estimate that you were making somehow, or is it more subtle?
So it is more subtle than that. So there is a TC which you can find from this estimate, which also depends on the filling, and I will discuss this in detail later.
Okay.
But it also depends, like, on other things which I haven't really talked about. So one of them is, like, once we start having a finite density, then there is inter 2e Scurmion repulsion, which also needs to be taken into account. And there would be a point when that repulsion can become too large if you are at too large filling, and some competing state can win over.
Like a Wigner crystal potential. Like if I go to very low density of these 2e objects.
If you go to very low density, then there is indeed a possibility of a Wigner crystal. We do see something similar in the DMRG numerics as well.
Okay.
It really depends. Like, it's a competition between this J term and, like, the anisotropy term. Of course, you are right. if there is no anisotropy, then there will be pairing, but there will be no phase coherence. If at very low filling, you will need some certain density of it to have phase coherence.
Sorry, would the effective Hamiltonian of the very lightly doped system be Jellium?
For the very lightly doped system?
Yeah, like, is it not, just the usual case of arbitrarily charged?
So there are some subtleties here.
Interacting.
So like one subtlety is that like when you are thinking of a Jellium model, of course, there is no lattice. So you have extended states in momentum space, but you could localize those states by constructing wave packets. Like here, because you are working with a churn band, there is a certain limit up to which you can localize them, but not more. So I think just describing it in terms of Jellium is probably not very accurate.
Got it.
But I agree with you that at very low densities of these charged 2e objects, and also as Debanjan pointed out, it could be a Wigner crystal. Yeah, we do see some evidence of that physics, which I might refer to later. For now, let me just move on.
But anyway, the lightly doped system would be a very large RS, basically.
Yeah. All right. So with this physical picture in mind, let's discuss whether this has some possibility of applying to magic angle twisted bilayer graphene. I won't spend too much time on this slide because I'm sure all of you guys have seen this picture enough number of times. But just to summarize it in one sentence, there is a Mott insulator at 2 out of 8, like 6 out of 8 filling, or 2 out of 8 filling, where there's an additional degree of freedom coming from layers in magic angle TBG. And when you dope it, you do see superconductivity. That's my summary. And if you have more questions, I'm willing to answer them. But for now, let's move on to see whether this picture can apply. So usually when we think of strongly correlated systems, which can be relevant to this kind of MATBG structures because they have very small bandwidth for the low energy bands, there are two kind of perspectives which people are usually used to thinking about, or two paradigms rather. One of them is the Mott-Hubbard paradigm, where one tries to construct a one-year description for these flat bands and add some interaction on top of that. And the other kind of paradigm is the quantum Hall perspective, where you don't have localized linear orbitals, but you can still get interesting correlated states because of interactions. Okay. So here I will take the second approach and briefly motivate it, although I will admit that it's unclear to me whether this is super applicable to twisted bilayer graphene. What it does very well, as Eslam and Nick found, was that it gives a way to organize the perturbation theory in a way to separate different energy scales. So that's why this approach, I think, is a good approach to take. Okay, so in order to take this approach, one has to go to this so-called chiral limit and perturb away from there. What is this chiral limit? So imagine this twisted bilayer graphene, but add some lattice relaxation on top of that. So graphene generally prefers to be Bernal stacked or AB stacked for bilayers, which means that these AB regions are expanded relative to the AA regions in the experiment. And as a result, when we consider interlayer hopping, we can take this into account phenomenologically by just reducing the AA or BB hopping term, which is W0, relative to the AB or BA hopping term, which is W1. So in the original paper by Bitstritzer and McDonald, they took these two terms to be equal, but phenomenologically, a lattice relaxation can be modeled by taking them to be non-equal. And we can take this to the extreme limit, although this is not strictly applicable to TBG, which is this chiral limit, where I just turn off the AA hopping. So I set W0 to 0. And in this case, there is this additional chiral symmetry, which is very similar to graphene, because I only allow for AB hopping, both in between layers and also within the same layer. And what this allows for is a sublattice and valley polarized basis, because the Hamiltonian anti-commutes with sigma z, which is the Pauli matrix in the sublattice space. So this limit, as was initially shown by this paper, very nice paper by Tarnopolsky et al. And also commented on by other papers, has some very nice properties. So first of all, one gets exactly flat Chern bands, where each band basically behaves like a lowest Landau level. So let me forget about spin for the time being and just focus on the valley and sublattice degrees of freedom, which reduces the total number of low energy bands from 8 to 4. Like you can think of this as taking some spin polarized limit or some spin valley locked limit if you want. That's the setting in which it's simplest to sleep this. So I have bands which are labeled by valley and sublattice, and there are certain crucial symmetries which relate these bands. For example, bands within the same valley but on different sublattices are related by C2T, where C2 is just 180-degree rotation above the z-axis and T is time reversal. So applying both of them together doesn't flip valley, but flip sublattice. Bands in opposite valleys and opposite sublattices are related by C2Z, because C2 flips both valley and sublattice. And these symmetries make all these 4 bands degenerate in this particular limit. So we can think of this 2 different Chern sectors made of Ka, K prime B, which has an isospin degree of freedom, which allows free rotation in between them, and then a complementary opposite Chern sector, let's say Chern -1 with Kb and K prime A, which sees the opposite magnetic field. So now we can add back dispersion, and dispersion introduces antiferromagnetic super exchange between these Chern sectors. So initially there was an enhanced U2 cross U2 symmetry for free rotation of spins in each Chern sector. But introducing the dispersion breaks this down to U2. And there are other further anisotropies which will reduce this further. But at this point, we can already see that this effective Hamiltonian just resembles weakly dispersing isospinful Chern bands, and with opposite antiferromagnetic exchange between the 2 different Chern sectors, which is precisely the setting we were discussing earlier. So I want to give kind of a schematic overview of how to arrive at this, since I kind of made a bunch of approximations which I should lay down cleanly. So we first start with these 2 weakly dispersing bands in the 2 valleys, and then we move to the chiral limit, where we can label these bands by valley and sublattice. And in this limit, they also carry certain Chern numbers. So now we reorganize this to group together the Chern +1 bands and Chern -1 bands. And note that these are all related by symmetries, so they're all degenerate at this stage. After this, we think of interactions where within each Chern sector, there is some polarization, some spin polarization. And then we add back the hopping, which says that, okay, now we have some n+ dot n- interaction in between opposite Chern sectors, which favors an antiferromagnetic super exchange that sets n+ to -n-. This is the Kramer's intervalley coherent state, or a valley Hall manifold. So let me explain these 2 terms a bit. So at this level, my n vector is still free to move in the Bloch sphere. And if it points along the north pole or the south pole of the Bloch sphere, then valley is still a good quantum number. So this is the valley Hall state, where I have one valley, let's say in Chern 1 and the other one in Chern -1. And that would not have any net Hall current, but it would have valley Hall current. It's like a topological insulator. Then I could also have a case where this arrow n points along the equator of the Bloch sphere, And this is what turns out to be the case when one adds further interaction terms, which I haven't discussed. And it's a bit hard to discuss that intuitively. So for now, I would just request you to accept my word that the actual interactions favor this state where this vector is pointing along the equator of the Bloch sphere. And this you can kind of think as an easy plane antiferromagnet. It's also IVC because I am non-trivially hybridizing between the two layers when I point along the Bloch sphere. And it's Kramer's because there is an additional Kramer symmetry, which is preserved by this state. So we did establish that there is the requisite band topology for this physics in magic angle twisted bilayer graphene. But topology is not everything. Energetics is very important. So even if there is the requisite band topology, if it just turns out that my Scurmions cost a large amount of energy, there is a large strain stiffness, then they are just not favorable charge excitations and we can forget about them. So we do need the stiffness to be kind of small for this physics to work. And we can calculate the stiffness. It turns out to be of the order of 1 MeV, which is not too bad, because what we can compare here is the ratio of the energy cost for two charge 2e Scurmions, which is just 8 pi times the stiffness, to the gap of the KIVC order parameter. So if this gap is smaller than the energy created to two charge 2e Scurmions or two charge e Scurmions, let's say, then I would just have regular particle hole excitations. Whereas if it is smaller than 1, then Scurmions would be favorable. So from Hartree-Fock numerics, we can get this delta KIVC and plot this ratio. In the idealized limit, this ratio is much smaller than 1. But if we go to the realistic limit, this is actually around 1. So Scurmions are, to some extent, energetically competitive, but it really depends on the details of the band structure, etc., as to whether they are energetically favorable or not. In particular, once we add on the other anisotropy energies to the stiffness energy, for example, the fact that we also have some exchange energy cost and some Coulomb energy cost within the semi-classical theory, we find that there is some tiny pocket where the charge will actually first favor to go in as electrons. And beyond that pocket, denoted in blue here, charge will go in as Fermions.
Shubhayu, question. I might have missed this. So the rho s that you're talking about here, this is the stiffness associated with the Scurmion, right? Not the pairing phase stiffness.
Yeah, right. So
okay.
this rho s is the stiffness associated with the IVC phase, to be more precise. So
okay. And the other question is, so when you say that the charge enters as 2e Scurmions as a function of some tuning parameter, whatever it is that you're changing, is it clear that the point across which the 2e Scurmions becomes the cheaper excitation, the pairing stiffness will automatically be finite so that this will be the superconductor?
You're asking if it's a first order transition into superconductivity?
No, I'm asking if I can have a completely phased in coherent, I guess, metal or a failed superconductor where the cheapest excitations are still 2e Scurmions.
Right. So we can compute this phase stiffness within some CP1 model where it turns out that that's the case. Like it is basically proportional to the density there. So I would imagine that that's the case, but beyond that, I would say not very controlled calculation because we are forced to take larger and whatnot. It's not obvious to me whether there will be a finite phase stiffness. I would expect so though, at least from DMRG, beyond the complications of TBG, we do see a superconductor.
Well, in DMRG, do you actually calculate the stiffness or you just calculate the pair-pair correlations?
We can actually estimate the pair mass. So I probably won't have time to talk about that, but we can actually estimate it. Yeah.
So just to be clear here, saying, before you hit this critical doping, the cheapest excitations are just your electrons.
Right.
and the charge E Skirmion is energetically unfavorable. But then beyond this critical doping, the binding energy between the charge E skirmions is such that the charge 2e skirmions become competitive or maybe even favorable over, the electrons.
Right.
And as soon as they become energetically more favorable, they also seem to have a finite superconducting phase stiffness, and the thing becomes a superconductor.
Yeah, that's the expectation.
Okay.
So maybe one comment here is that it could also be that charge E skirmions are favorable. Like for that, we need to compute the other anisotropy anisotropy energies to the stiffness. So without the anisotropies, the charge E energy is just charge 2E energy is just 2 times the charge E energy. So it's this exchange energy which makes charge 2E favorable. So it could also be that in some part of the phase diagram, charge E excitations are favorable, but that wasn't of that much interest to us, so we didn't actually compute it.
And does your TC, or the actual superconducting phase stiffness, that is proportional to, some energy scale times C, the actual Chern number, correct? Like the Chern number does enter through the topological charge.
Yeah, the Chern number. So I would say that the Chern number enters more specifically through the superfluid stiffness. Right. Because if you go to higher Landau levels, then this physics is not seen anymore.
Well, okay, that's what I was going to ask. I mean, if I just take Chern number 2 setup.
So there, what happens is that, very crudely speaking, the Chern number, the superfluid stiffness is proportional to Chern number squared. So the Chern number just jumps by a factor of, or the superfluid stiffness jumps by a factor of 4 when you go from Chern 1 to Chern 2. And that already makes Skirmions very unfavorable. I mean, you could still design some interaction which would give rise to such superconductivity, but then you could also argue, as I will discuss later, that maybe that interaction by itself is sufficient to give superconductivity. No collective pairing mechanism, as we are discussing, is required.
Okay, sorry, I guess I've been asking too many questions. I mean, do you know how far along the talk you are right now?
I mean, I can't. So I guess since there is not too much time, I will just discuss MATBG, some curious. So I'm going to discuss some curious theoretical features of this model, which some of you guys might like, and then have a brief do to twisted trilayer, mirror symmetric trilayer, and then end there. Maybe not discuss DMRG unless there are further questions.
Yeah, I mean, given how many questions I have asked, I think you can take maybe 15 to 20 more minutes for sure, but I'll probably stop asking questions.
No, that's fine. These are all excellent questions. So keep asking. I think I have always felt that it would be too rushed to give present all of this in a 1 hour talk. So there are certain ending points which are natural, and I will just end there.
Yes, sorry, maybe I should maybe just add something real quick. So you have 2 lines, ideal and realistic. So ideal is something that you found by changing, randomly exploring the parameter space, or you have some information like that?
Yeah, there is no strict criteria for ideal. So the definition of ideal for us was that
well below
to
1.
what extent we can push up this ratio W0 over W1 such that this ratio of Scurmion energy to particle hole energy gap still remains around half, which is what you expect for a 0th Landau level, basically. So we showed that we could push it up to around 0.3 and still it remains pretty close to half. But once we push it up beyond that, then it starts going up.
I see. Okay.
And the realistic is some data taken from Carrot all basically DFT numerics. Although from latest information, this W0 over W1 is somewhat large because they have figured out some apparent bug in their code or whatever, which makes it slightly smaller. So that's good for us, I guess.
Okay.
But it's not as small as 0.3. It still will be 0.6 or 0.65.
Thank you.
All right. Yeah. So I want to discuss some theoretical formulation for the doped phase diagram a bit by taking kind of a detour from specific materials, because that is kind of cool. So one way of thinking about this particular phase transition between an insulator and a superconductor at zero doping or at finite doping is to write this n vector in my antiferromagnetic or spin valley locked manifold as CP1 in terms of a CP1 vector. So I take my vector n and write it as z dagger eta z, where eta is just Pauli matrix and z's are bosonic two-component spinors. So doing so naturally introduces a local gauge field, which corresponds to local phase rotations of z. And something very nice is that in this formulation, the charge density can be written as just the curl of this emergent vector potential. So here, if we form a Scurmion, that can be thought of as a flux or vortex of A that carries U1 charge 2E. But note that we can also write the superconductor, the real and imaginary parts as N4 plus IN5. And we can have an alternate CP1 formulation where instead of combining N1, N2, and N3, we combine N3, N4, and N5. So N3 here corresponds to the North Pole and the South Pole of the Bloch sphere, which I was discussing earlier. So that's this Valley Hall phase. And N4 and N5 are the superconducting, real and imaginary part of the superconducting order parameter. And one can also ask the similar question of what is the physical implication of the gauge field for this CP1 theory in terms of M rather than N? And it turns out that the curl of this gauge field is basically the valley flux. So if I have some vortex in this gauge field that carries valley charge, which is U1V. So these two act as kind of mutual defects of each other. So on one hand, on the left-hand side, we can have this IVC insulator, which I can think of in terms of this language as having the A vortex gapped, which is to say that my charged excitations are gapped and it's an insulator. But my AV or valley vortex is condensed, which means that I have broken the U1V symmetry. On the superconducting side, exactly the opposite thing happens. My A vortex is condensed, so my charge 2E pairs are condensed. And my AV vortex is gapped, which means that I have restored this U1 valley symmetry. And at zero doping, the transition in between these two is mediated by this easy plane version of the deconfined quantum critical point, as studied in previous papers by Senthil et al. And Wang and Nahum et al. So I introduced this language because it's kind of helpful to think in terms of the spinors to describe the doped phase diagram. So earlier we were just restricting ourselves to the z-axis or the vertical line in this plot. So we're remaining at zero doping, and we could imagine tuning interactions such that at large interactions, large repulsive interactions, there would be an insulating phase. And once we go beyond the critical value, or go to small enough interactions, there would be a superconductor. Now we want to do something else. We want to go along the horizontal axis. Let's still set T to 0 and go along the mu axis. So in this language, what happens? Of course, at mu equals 0, we start with the KIVC insulating phase. And in terms of the CP1 language, we can describe this phase as having Zi condensed for I equals 1, 2, and also Z1 star Z2 condensed. Because remember, my KIVC order parameter was pointing along the equator, which basically means Pauli matrices X and Y are condensed, which is Z1 star Z2 in the CP1 language. So because these Zi's are condensed, the vortices in A mu, which are charges, are disallowed. This gauge field is Higgsed. So my charged excitations are costly, and this is an insulator. So now we imagine turning on the chemical potential. And now this chemical potential acts as a magnetic field, because this chemical potential basically couples to the charge density, but recall that the charge density was just the flux of this emergent gauge field. So it couples directly to 2E Scurmions. Of course, these 2E Scurmions had a certain gap, so it doesn't immediately favor to proliferate these 2E's, but beyond a certain critical value, which within the large N theory is actually just equal to the value of the gap of these 2E objects. Beyond this critical density, it favors these 2E Scurmions. So one way to think of this is that my ZIs are no longer condensed because I have proliferated defects. So my A mu is now in Coulomb phase, and that allows for charged excitations. But Z1 star, Z2 can still be condensed because the relative phase can still be well defined. So this is a region where we expect some coexistence between this IVC phase and the superconducting phase. And on further raising mu, we expect that the IVC phase amplitude gradually goes down, and then this state becomes just a superconductor where both Zi and Z1 star Z2 have 0 expectation values. And my A mu is in a Coulomb phase, so charge excitations are cheap. So that's what happens at t equals 0. At finite t, there will presumably be BKT transitions out of this phase. So we tried to see if we could recover this theory within a semi-controlled large N calculation where we generalize CP1 to CPN. But unfortunately, it turns out that that's not the case. The large N theory just gives a direct first order transition. So we start with the KIVC phase, and beyond some mu equals mu critical, we end up in a superconductor with no KIVC. And this is kind of an open question, I would say. We don't know how to find as controllable or solvable model where we can see the phase coexistence yet. So one other thing which the large N theory can estimate is that we can estimate TC within this large N theory, and that is proportional to J times the density. This just
Shubhayu, just one question. So this TC is estimated from the stiffness. What is the actual amplitude scale? What is that set by? J or?
Which particular amplitude scale?
So the pairing gap, what sets that? What energy scale sets that? I missed that.
Yeah, the pairing gap is set by J.
Yeah, okay. So there isn't like a parametric separation between the two scales. They're both set by J.
Yeah, there is no parametric separation.
Yeah, okay.
So BEC limit, if you will.
Yeah, kind of. That's right, Sam. It's kind of a BEC limit. Because this picture is also kind of a very real space picture, at least when thinking in terms of spins. Okay. All right, so finally, I guess I would like to mention potential applications to a different other platform, which is magic angle twisted trilayer graphene, which also has been shown to superconductivity. So it's the so-called graphene sandwich where you take the middle layer and you twist the bottom and top layers with the same twist relative to the middle layer. And that has certain symmetry consequences. In particular, it preserves some C2D symmetry. And in this case, people have already worked out the band structure. And it turns out that it decouples into a single graphene monolayer plus a TBG like flat bands near charge neutrality. So I don't have very good intuition for this. I would be glad to hear from you guys, like why this is the case. But at least formally, this is what comes out. And also, given that we have TBG like flat bands, we can ask this question: when are the bands flattest? And because the hopping between, like the effective hopping in the TBG subspace is larger by a factor of √2, basically, it turns out that the magic angle for twisted trilayers is square root 2 times the magic angle for twisted bilayers. So there have been fairly recent experiments, both in Pablo's group and in Philip Kim's group, where robust superconductivity has been observed in magic angle twisted trilayer or mirror symmetric twisted trilayer. And there are several evidences that this is a strong coupling superconductor. Like one evidence, for example, is that the superconducting coherence length is small. So if you kind of interpret that as roughly the size of Cooper pairs, it means that the Cooper pairs are tightly bound Of course, this interpretation is only valid for S-wave superconductors as far as I understand, and it's unclear whether their superconductor is S-wave or not. But if we assume that, then that is fairly strong evidence for strong coupling superconductivity. And one other feature which they kind of observe is that this TC away from half-well state is kind of linear in the doping, which indeed falls out fairly simply out of our model. So that's some hint perhaps that maybe some of this physics is at play in magic angle twisted trilayer.
Wait, Shubhayu, I mean, TC proportional to doping has got nothing necessarily to do with Scurmions, right? They're like a doped mod insulator would also, to the extent that it has pairing, would also have TC proportional to doping away from the insulator. Like I missed, maybe there's something in the logic, but just the TC proportional to doping doesn't mean much about whether it's from Skirmions or something else, right?
Well, I mean, you would say that you could get it in a theory where you can look at, like, I know how to get it from BEC-like theory. So in that sense, it doesn't matter whether the charged objects are Skirmions or something else. Maybe I'm not just aware of this literature that like you can, like, if you start with a Mott insulator, I guess as long as you have pairing, you can still get TC proportional.
So the classic, the 89 theory for like the, you know what this means when I say that, right? The mean field theory for the doped Mott insulator in the cuprate, the TC would be proportional to delta away from the Mott insulator. So, I mean, you can question the theory, but by itself, that's not.
Yeah, that's a fair point. Yeah. Yeah, so I guess with other constraints coming from symmetry and band topology, one might argue that physics might not be relevant here, but of course it doesn't mean that this is what is going on.
Yeah, I mean, I was implying the flow of the logic. I mean, I'm not saying that that's what is happening here, but.
Right. I guess you can have, sorry.
I just want to be clear. So once these Skirmions pair, do they have any quantum numbers left or topology left?
They do have some quantum numbers left. So they don't transform non-trivially under this isospin degree of freedom because they're antiferromagnetic. So in that sense, it's an isospin singlet. But you can ask other questions as to, for example, how do these transform, for example, under gamma z times spin rotations, isospin rotations, and they do have quantum numbers under those symmetries of the problem. So it's a bit technical, which is why I didn't discuss it here, but.
But let me actually, I want to be very clear. So the question on my mind is this a different phase than a standard charge 2e superconductor? So if the Skirmion pair had no quantum numbers left, that would be exactly an S-wave pairing, singlet pairing, right? If the Skirmions pair and have no quantum numbers left, then that's the same phase.
Right.
So the question is, what quantum numbers are left within the problem, and more importantly, what quantum numbers are left within the actual Hamiltonian, right, without the enlarged symmetries that you've used.
I see. Okay, thanks. That's a very good question. So maybe I will try to answer this by asking the following question. So to answer this, we have to ask how does the Skyrmion pair transform under the different symmetries I have in the problem? And are these transformations different from what I would have if I just had an electronic Cooper pair instead of a Skyrmionic Cooper pair? Is that the kind of question you were getting at, Sam? Like, did I phrase that right?
Yeah, I want to know the distinctions. the sharp distinctions between Skirmion pair and standard Cooper pair.
I see. So as far as that sharp distinction is concerned, I think there is no such sharp distinction, because the quantum numbers which are left after the formation of the pair are basically the quantum numbers which says whether it would be layer singlet or vary singlet or layer triplet or isospin triplet. But things of that kind, you could also just formulate for electronic pairs instead of Skyrmion pairs.
Okay, so there would not necessarily be any phase transition between an S-wave superconductor and a Skirmion paired phase.
Right. Like you could, as far as symmetry is concerned, like you might as well treat this superconductor as a plain vanilla S-wave superconductor.
Okay.
Like the distinction mainly comes from energetics and how the superconductor comes to be. But once it's there, I don't see a strict distinction. Like if there were preformed pairs or something, maybe like there would be some way of detecting it, but I don't know. It's a hard challenge for me to figure out.
So it bears very much on how to, detect to really establish or confirm.
All right. Okay. So I guess I've probably overrun. So I had some sections on whether this Skirmion pairing actually works in real life. For that, we did some DMRG, and maybe I will just flash the phase diagram of the DMRG to first show that there is some superconductivity. So let me just directly go to the phase diagram. Yeah. So here we studied this projected zeroth Landau level model within DMRG as a function of J, which recall was the isotropic antiferromagnetic exchange. And lambda, which was the anisotropy between easy plane and easy axis. We studied it for lambda greater than 0. And what we found was that indeed for a finite value of J at doping 2 + 1/4, there are some technical problems for going to lower doping than this. This is the lowest doping which we could realistically do. We do see some superconductivity in the pair correlations. And one thing which we can establish is that the superconductivity is almost certainly due to Skirmions. And we do so by looking at energy of charged pairs, which we can also compute within DMRG on top of the insulating state. So within DMRG, we can start with an insulating state, put charge E or charge 2E as we want, and ask what is the energy of the resulting state. And using that, we can establish that if we have at large J and small lambda, for example, this delta pair is actually greater than 0, where I have defined delta pair as the difference in energy between 2 1E and 1 2E excitation. So delta pair greater than 0 means that pairing is favored. And if we extrapolate this result to Ly, which is the circumference length of the cylinder to infinity, we find that pairing is indeed favored at 0 anisotropy, even for J going to 0. However, for DMRG, we can't really go to very large system sizes. We are limited to in the circumference of the cylinder by large entanglement growth in that direction. And we can ask, does this critical J at which superconductivity is seen also compare to the critical J at which pair formation starts becoming favorable? And the answer actually does turn out to be yes. So we can do a relatively cheap computation of just looking at pair energetics at 0 doping, and that is somehow predictive of the phase diagram of the superconductor in this J lambda plane at finite doping, as we have kind of shown here. Of course, there are interaction effects in between the Skirmions, which we haven't taken into account. So it's somewhat crude, but it still shows that this theory does have predictive power. All right, so with this, let me just outline my conclusions. So we have numerically kind of established that there is a Skirmion anti-Skirmion pair condensation mechanism, which can give rise to superconductivity, and band topology does play a crucial role in this, we repeated this DMRG with bands having the same Chern number as opposed to opposite Chern number that you can take as a control experiment where we didn't see any of this physics. And perhaps magic angle twisted bilayer or twisted trilayer has the right physical ingredients to realize this mechanism. They have the required band topology and low isospin stiffness. However, this is not restricted to these materials. In general, there are a lot more new materials coming up which have Chern bands. And if one can engineer the correct kind of tunnel coupling between those bands or even work with some other quantum simulators, one can presumably see this behavior. So it's more generic than these materials. So there are several open questions, some of which I'm working on, and I would be glad to get your inputs on. So one of them is the effect of non-uniform Berry curvature, which we didn't have to deal with within the Landau level DMRG. So that I think can be really answered by doing DMRG on the actual model, which is a very complicated project as it requires bond dimensions of 100,000 or so. The other more qualitative, or maybe something which can be answered with lesser computational effort, are the effects of disorder on this kind of pairing. Also the effects of spin orbit coupling, because there are some papers which don't find any insulating states, but still do see superconductivity. So it could be that superconductivity there has a different origin, but it could be that the same mechanism in some guys also functions there. So that's another open question. All right, so with that,
how about pairing symmetry?
So the pairing symmetry is something we can calculate within this mechanism. Again, like the simplest Skirmion pair we can get is an isospin singlet, but a spin triplet. So it's kind of like S wave. There is, in the sense that the charged objects really sit on top of each other, there is an additional like Chern sector degree of freedom or layer degree of freedom if you weigh in which the wave function is antisymmetric, so it can still be symmetric in spin. So it's symmetric in real space, symmetric in spin, and not symmetric in this additional layer degree of freedom. But given a particular Skyrmion superconductor, we can calculate its pairing symmetry. This is detailed in the paper with Eslam and Ashwin, and also in the other paper with Mike and Nick. So if your question is whether we can predict the pairing symmetry of TVG, we have some prediction for it, but we don't know whether that's right or not. But if your question is whether we can calculate a pairing symmetry for a particular Skirmion paired superconductor, the answer is yes, we can do that. If you give me a particular Skirmion pair, I can actually calculate its quantum numbers under different pairs. And from there, I can infer the pairing symmetry of the resultant superconductor.
All right, so let us all first thank Shubhayu for an excellent talk. Shubhayu, there were a lot of people here. It's not just whatever, the 7 of us still holding on, but I guess we ran over and they had to leave. So Cyprian has a question, it seems, for you.
Yes, sorry. Thank you for the talk, but so I have two experimental questions. So one is, if you were to imagine measuring tunneling conductance into the sample, I would imagine that in this BC regime that you that your air charge 2e excitations are the lowest energy excitations. You will not expect to see coherence peaks. Is that true?
Right. So that is certainly correct if the edge doesn't violate any symmetries which we are talking about. So somewhat, I don't know whether fortunately or unfortunately, we did start talking about valley as a good quantum number to start with, and the edge breaks this symmetry. So there is this question about whether the state we start with is a topological insulator or not, and whether we will see edge states. And morally, it is similar to a topological insulator, but because one of the symmetries which protects it is violated at the edge, like there may not be any edge states. So in a similar spirit, because this symmetry is actually gone at the edge, for this particular material, it is unclear to me whether you will see specific signs in the edge conductance, in the tunneling edge conductance of 2E versus E excitations.
So I mean here that in a conventional BCS theory, you see the coherence peaks because you open the gap at the Fermi surface. Your system becomes a quasi A1D, and then you have the divergence near the edge of your system. So here I thought that you first open the gap, right, and that's why your system would not be quasi A1D.
Yeah, I think you were talking about two different edges.
Yes.
Shubhayu, you were referring to the physical edge of the sample. He was talking about, the thing that you see at, in the standard BCS picture, the coherence peaks.
So tunneling conductance,
yes,
has a peak at the gap.
Exactly. Yeah.
I see. Okay. Sorry, I misinterpreted what edge meant. Thanks for the clarification. So here, I mean, if you do, like, there is this concern that it is really a 2D superconductor, right? So at least realistically, there is no tunneling gap or tunneling edge in that sense, because.
Wait, what do you mean? I mean, deep in the superconducting state, like at very low temperatures.
I mean,
if it's
okay. So there is the ideal limit, and there is perhaps a more practical limit. The ideal limit is where, like, at any finite temperature, you only have quasi long range order and not long range order, because it's a BKT transition. Like, you could argue that the coherence length becomes so large that it doesn't matter for all practical purposes, right?
Yeah.
Like in that regime, yeah, I'm not sure. So in that regime, I would expect to see some signatures, but then the question was whether I would see different number of coherence peaks for 2E versus E, Cyprian, or what?
Yes, so I'm thinking of it if your ground state before you have superconductivity is conventional Fermi liquid or something like that, then you should see the conventional peaks from BCS theory, maybe somehow changed. But if your ground state is something which open the gap and then you have superconductivity, then you will not see the peaks.
Right. Actually, if I can just jump in, I had a related question, which is, I mean, in this charge 2E Scurmion picture, like if you go above TBKT, what is that state? I mean, it's a metal, but I mean, do you know anything else about what that metal is supposed to be doing?
Not really. I mean, it should have both charge E and charge 2E excitations. So
I thought
it's a very interesting state.
I thought you said the charge E excitations are gapped.
So are the 2E.
No. Well, no. The 2E, I mean, there's a binding energy. The charge 2 excitations are gapless, and then they develop phase coherence below TBKT.
Okay. So you were talking about, okay, so I was confusing with the realistic bilayer graphene picture I showed, where there were also gapless charges, but you are talking about a more simplified scenario where the charge 2Es are the only gapless ones and charge Es are gapped. Yeah. So that will be like a.
I think it's a pseudo gap metal.
It would be a state with bosonic charges doing transport. I haven't thought much about this.
I mean, no, but I mean, I think it's a pseudo gap metal in the sense of it.
Like if you do electronic spectroscopy, or RPES, then yeah, you probably won't see. Okay, so.
Or wait a second, no, sorry. I think you said, didn't you say that? I mean, okay, this is in the devil is in the details, but you said it's a spin triplet, like the physical spin. It's not a spin
physical
singlet.
spin could be a spin triplet. It also could be something like spin valley locked, where they're pointing in opposite
Okay,
directions.
so if it's spin triplet, then there is no necessarily a spin pseudogap, but okay, it's complicated.
But so there would be, of course, charge E excitations thermally excited at any finite temperature as well, right? But just above TBKT, I would expect them to be much more, depending on what TBKT is, I would expect maybe that they are much smaller in number than charge 2e bosons, which are moving around. So this is kind of an interesting question, which I have been thinking about off and on, which is like how these Scurmions 2e objects dissipate energy into these charge E objects as they move around. And I would be glad to get any kind of input or help if someone wants to think together with me on that.
Not just energy, right? Also momentum.
Yeah, also momentum. So I think it's a very cool problem, which I just haven't spent enough time thinking about, but it's.
And sorry, I didn't mean to distract from Cyprian's question, but I don't know if actually that.
Yeah, maybe like Cyprian, probably I didn't answer your question, right?
I mean, indirectly you did, because you also mentioned that you also will have a conventional air charge E excitation. So maybe it's somehow mixed. How will your DIDV look like? It's just it's this. I mean, it looks like a good experimental signature, especially of this BC.
Yeah, that's certainly a very interesting point. I hadn't thought about this, but it would be interesting to investigate.
Okay, and then I have a second one, and this is on the same topic. It just may sound very specific. So in cuprates and in ion oxides, when you measure DIDV, in addition to the coherence peaks, you see on both sides so-called deep humps. And these deep humps are indicative of a coupling, of a decay into bosonic excitations at these characteristic energy scales. And my question would be whether you would expect similar mechanism that somehow you decay into these Scurmionic excitations, and if so, you would produce such features in your DIDV, or you think the situation would be different?
So maybe explain to me a bit more. So you were studying DIDV
actually,
as a function.
If I could just stop. I mean, Charming, I don't know. Did you have another question? Because it seems like a few of us have hogged all of Shubhayu's time.
Yeah, I kind of want to ask about something different, but the.
I mean, I'm happy for this to continue. I just wanted to make sure.
Yeah, I don't have like I mean, yeah, I'm happy to listen. So go on, please. Yeah.
Yeah. So maybe let me try to understand this a bit more, because I might not be super familiar with this literature. So you are plotting DIDV as a function of voltage, and you are saying that, like, in addition to peaks at certain characteristic voltages, there are also additional peaks in the DIDV curve which come from dissipation of what object, like Cooper pairs into some collective modes, or electrons into some collective modes?
So it's the decay of electrons to a collective mode.
I see.
Give me a second to.
Charming, should I stop recording? I guess I never stopped.
Yeah, I think there is no point.
Yeah.